Hi everyone, my name is Andreas Niskanen. I'm a postdoc at the University of Helsinki, working at the Constraint Reasoning and Optimization Group. I'm currently funded by the Research Council of Finland. So I'm here today to talk to you about the main topic of my research, which is automated reasoning, developing both generic methods for automated reasoning as well as applications of automated reasoning in different contexts. So without further ado, I'd like to start with some motivation. In many real-world application settings, it is a key requirement that we obtain both provably correct answers to questions, as well as, in certain situations, proofs that a solution to a problem does not exist. These include both hardware and software verification problems, automated theorem proving, for example, if there are mathematicians in the audience, as well as scheduling and timetabling problems, problems in bioinformatics, information security, and many others. All of these contexts give rise to so-called NP-hard computational problems. And for a concrete example, we can think, for instance, about we have designed a piece of hardware that we'd like to start producing, right? If we would like to verify that this hardware works correctly, because if we start producing it massively, and then it turns out that given a certain sequence of actions from the user, the hardware circuit enters an undesired state, this would cost us a lot of money, right? Alternatively, you can think about software which is used in safety-critical applications, such as medical or aerospace industries. So in this kind of a setting, we would formulate proving this correctness as a search problem. So find me a sequence of actions so that this hardware circuit enters an undesired state. And if such a sequence of actions does not exist, well, that's a good thing, but we'd like to be very, very sure of it. So we would require a proof of this fact that the sequence does not exist, right? Alternatively, if such a sequence exists, we would like to extract it and to analyze it further, right? So, what makes this thing called automated reasoning a reality is a key technology named Boolean satisfiability, or SAT. In theory, it is a so-called NP-hard problem, which means that it's computationally intractable. So no algorithm exists which would solve SAT efficiently on arbitrary input instances. It has been studied very broadly in theoretical computer science. In contrast to this theoretical result, in practice, there have been significant algorithmic improvements in practical SAT solving since the early 1990s. So modern SAT solvers, which are actual pieces of software which solve SAT, are able to solve instances with even millions of hundreds of millions of variables and constraints, which is a lot. This is mainly thanks to various algorithmic improvements, notably the so-called conflict-driven closed learning, or CDCL algorithm. Modern SAT solvers are also able to provide both explanations and verifiable proofs of unsatisfiability. They also offer so-called incremental interfaces for solving a sequence of related instances. So if we want to solve a sequence of instances, we only need to instantiate the SAT solver once. And then we can use its API to modify the internal instance while keeping the state of the solver, including learned information, with the hope of speeding up successive calls to the solver. So now that we're done with the introduction, let me cover some of the main methodology and techniques that I've been using in my research so that you will maybe understand the applications a bit better. So let's fix some terminology first. Computational complexity theory in general studies the resource requirements, that is time and memory, spent by different algorithms. And it turns out that different computational problems can be classified into these so-called complexity classes according to whether an algorithm exists which satisfies a given set of criteria. One of the most well-known complexity classes is P, which is the set of problems computable in polynomial time. This is regarded widely as efficiently solvable or tractable. Another famous complexity class is NP, which consists of problems whose solutions, that is, yes answers, can be verified in polynomial time. And there are various classes beyond NP, including the polynomial hierarchy, P-space, or the set of problems solvable in polynomial space, which I won't go into detail here. So, in NP, we have this. So, NP-hard problems are deemed, in contrast to problems in P, computationally intractable. So they are at least as hard as the hardest problems in NP. In particular, for any NP-hard problem, no polynomial time algorithm currently exists, and it is very doubtful that such an algorithm would exist, as it would effectively resolve the P versus NP question. A characteristic of NP-hard problems are these so-called exponential search spaces, which prohibit exhaustive search over candidate solutions. For instance, just to give you an intuitive picture of what exponential search spaces mean in practice, if you think about a software verification task with 8 32-bit integers as input, the number of possible states that we can have is 2 to the power of 8 times 32, that is how many bits we have, which turns out to be around the order of 10 to the power of 77, which is pretty much an astronomical number since it's quite relatively close to the number of atoms in the observable universe. So there is no way we can enumerate all candidate solutions and try to find a solution to the problem this way. So, how do we solve NP-hard problems? Well, the main methodology I've applied in my research, and this is one of the main methodologies for NP-hard problems, there are others as well, is this so-called declarative problem solving paradigm. Essentially, first we select a suitable constraint language for a problem. So let's fix a constraint language, such as, for instance, SAT, which I've mentioned. And now we are left with 3 steps. The first step is to develop a so-called encoding, which is specific to the problem we're solving. This is a reformulation of the problem using the constraint language that we picked. So we develop an algorithm which models our problem as a set of mathematical constraints. For some concreteness, if you think, for instance, about solving Sudoku, everyone knows what Sudoku is, right? A constraint could look like for every row and for every number from 1 to 9, there must be an occurrence of this number on this row. And even more specifically, exactly 1 occurrence, right? And the same for columns and these 3 times 3 squares, right? Then, now we have an algorithm which transforms our original problem into this constraint language. And the second step is to call a constraint solver, which is generic for that constraint language, which is our automated reasoning engine. Essentially, it is a search algorithm for this constraint language and implementation thereof. And this constraint solver either finds a solution which satisfies our constraints, or it determines that no solution exists. And in the case that it found a solution, the third step is so-called decoding. So we map this solution to the constraint instance back to a solution to our original problem instance. Right. Various different constraint languages and solvers have been developed. I already mentioned Boolean satisfiability, or SAT. It's a relatively low-level language based on propositional logic. And it's, as I mentioned, the archetypical NP-complete problem. So it's studied widely both in theoretical computer science as well as in practical terms. Various generalizations of SAT exist, including quantified satisfiability. If you're familiar with logic, it allows for existential and universal quantification, answer set programming, pseudo Boolean reasoning, etc. These different constraint languages have different kinds of expressive power, both in terms of the computational complexity of problems that they can efficiently cover, as well as different types of constraints that they allow. They also have slightly different algorithmic techniques, but for many of these more general paradigms, solving algorithms are based on either employing SAT solvers or similar techniques as in algorithms employed by SAT solvers. For optimization problems, that is, if in addition to satisfying a given set of constraints, we also need to find a best solution according to some criteria, be it cheapest, fastest, and so on. There are also optimization extensions of these languages. For instance, our group has worked a lot on the optimization variant of SAT, which is called MaxSAT. Okay? So let's stick with SAT for now. So if we want to solve a computational problem using the declarative method using SAT solvers, and our problem has beyond NP complexity, there's a slight catch, because the size of the SAT encodings tends to exponentially blow up, very much in a similar way as search spaces of NP-hard problems. So a suitable and maybe a suitable option would be to choose a different constraint language, which, for instance, allows quantification and thus covers higher complexity classes. In practice, however, iterative procedures, which make use of several SAT solvers as NP oracles, have been very successful. One example of such an iterative procedure is SAT-based counterexample guided abstraction refinement, or SEGAR. In SEGAR, we make use of two SAT solvers, and instead of constructing the encoding in a one shot, we essentially construct it step by step lazily. So we instantiate the first SAT solver with an abstraction of our problem, which essentially is an over-approximation of the set of solutions. Now this SAT solver gives us candidate solutions to our problem. Since we're dealing with an over-approximation, we do not yet know whether this candidate solution is an actual solution to the problem. So we're going to use a second SAT solver to search for a counterexample within this candidate solution. And if this SAT solver finds a counterexample, we analyze it, and we add a refinement constraint which rules out that counterexample to this first SAT solver. And we continue until either the first SAT solver reports that there is no solution, then there is no solution to our original problem as well, or the second SAT solver reports that there is no counterexample in this candidate solution, in which case we know that we have found a solution to our original problem. In practice, these kinds of procedures make heavy use of these incremental interfaces offered by modern SAT solvers, for instance, to iteratively add these refinement constraints without restarting the solver. And these kinds of speed-ups offered by incrementality are very important because, in general, for beyond NP problems, the worst case number of iterations of this loop is exponential with respect to the input. Okay. Now that I've covered some of the main methodologies I've been using in my work, I'd like to briefly showcase, actually, some of the applications that I've developed together with my colleagues, of course. So, for the first context, is argumentation theory. And this is, in fact, a topic of my PhD research. So, what is argumentation theory? Argumentation theory studies formal models for representing, constructing, and reasoning with arguments. And it finds applications, for instance, in legal and medical reasoning, where we often have to deal with uncertain or incomplete information. Argumentation can be seen as a form of defeasible reasoning. This means in practice that if I now accept a given argument, I might end up rejecting it if I'm presented with sufficient counter-arguments. So we can, in a sense, revert our position. From another perspective, it is also a form of common sense reasoning studied actively in modern AI. A central model for formal argumentation is that of abstract argumentation, where arguments and their counter-arguments are represented as a directed graph. So here we see an example of 3 arguments. There's an argument for the weather is sunny, the weather is rainy. These arguments are counter-arguments for one another, so there's edges in both directions. And then there's an argument for, hey, we should go play golf. Well, rain is quite an obvious counter-argument to playing golf. Given such a graph, different kinds of argumentation semantics have been defined, which identify arguments that are sort of jointly acceptable, so they jointly survive the conflict. So reasonable argumentation semantics for this graph might output that, well, the empty set is jointly acceptable, well, because it is possible that we accept none of these arguments. Rain, as a singleton, is acceptable. Then we don't accept golf, nor do we accept sun. Or you can accept that it's sunny and we should go play golf. Well, one catch here is that this graph is relatively simple, right? We can even enumerate all possible subsets, but in general, reasoning tasks in abstract argumentation are NP hard. For instance, deciding whether a given argument is accepted, that is contained in a jointly acceptable set of arguments, that's an NP hard problem in general. So, even before I started my PhD research, it was known that some of the most efficient algorithms for core problems in abstract argumentation, such as acceptance, are based on employing SAT solvers and other constraint solvers, such as ASP. What we've done is extend these ideas to various other problems, more complex problems, in abstract argumentation involving dynamics, that is, changes in the structure of this graph, uncertainty, so covering situations where, for instance, we don't know whether this argument has yet entered the discussion or not, as well as explanations, meaning that, well, in certain scenarios, instead of just knowing that, this argument is rejected, we might be interested in, well, why exactly is this the case? And preferably with like a compact explanation for this fact. Firstly, we've shown complexity results for various different problems and variants of thereof. And sort of guided by these complexity results for problems in NP, we've developed SAT-based declarative algorithms. For optimization problems, we've used MAX-SAT. And for beyond NP problems, we've developed both SAT and MAX-SAT-based SEGAR algorithms. We've also implemented these algorithms and empirically evaluated them. Here we have a plot, a scatter plot, where on the y-axis we have the running time of a SEGAR approach, and on the x-axis we have the running time of a QBF approach, which is this quantified satisfiability, another declarative paradigm. And we sort of see every point here is an input instance, and we sort of see that the approaches are complementary, since there are instances which SEGAR solves very quickly, where QBF times out, and on the other hand, there are instances which QBF solves quickly, but SEGAR times out. So they sort of complement one another. On to the next one, social choice theory. What is social choice theory? It studies collective decision-making scenarios where agents need to reach consensus, right? This often involves the aggregation of individual preferences or opinions into a collective preference or opinion. It finds applications, for instance, in decision support systems, digital democracy tools, etc. One of the central problems in social choice theory is judgment aggregation. It's a generic framework which covers, for instance, voting settings using preference aggregation. For an example, this might be an input instance to a judgment aggregation, rule, essentially. So think about a setting where we're hiring or an applicant is seeking funding. Now there are 3 experts with different opinions on whether this candidate fulfills research qualifications, teaching qualifications, and whether we should grant the applicant the funding. The first expert says that yes, excellent researcher. Well, teaching is a bit, so yeah, let's not grant the funding. The second expert is, well, research output is a bit blah. On the other hand, yeah, they're an excellent teacher, but this does not suffice, so let's not grant the funding. And the third expert considers this an excellent candidate overall. If we do the first thing that comes to mind, that is take the majority opinion, we end up with sort of a paradox, because according to the majority opinion, research output is excellent, teaching qualifications excellent, but we should not grant the funding. This is known as the discursive dilemma, and this sort of shows why this is a non-trivial problem. And this is why various different aggregation rules have been defined in literature. These are in general NP hard. So what we've done is design SAT-based algorithms for various NP hard judgment aggregation rules. And the key here is that many of these rules can be viewed as optimization problems with propositional constraints, making MAX-SAT a viable declarative approach. We've also implemented and empirically evaluated the algorithms, showing that, well, for most rules, we can actually solve almost all of the instances, while some rules remain harder to solve. We've also looked at more involved problems with strategic reasoning and designed algorithms for those kinds of settings. For instance, these problems can ask the question, is it possible to influence the outcome of an election? And for these, we've developed MAX-SAT-based SEGAR algorithms. So let me skip a few slides and conclude. SAT solving is a key technology in automated reasoning. The declarative approach allows for solving various different NP-hard problems using problem-specific encodings and generic solving algorithms. For beyond NP, iterative procedures such as SAT-based SEGAR have often been successful. For applications, we've covered argumentation and social choice, and well, hopefully there will be many more to come in the future. And at this point, I'd like to thank you for your attention, and sorry for being a bit over time.